So thank you all for joining the third Hybrid Systems seminar today. This is a part of a series of 4 seminars taking place this semester, where we're hearing from students, postdocs, and faculty from the community. So for today's seminar, we'll be hearing from 2 students in the community. So the format will be 2 30-minute talks. So up first, we have Emmanuel Jr. Wafo Wembe. He is a third-year Ph.D. candidate at the College of Computing in Mohammed VI Polytechnic University, supervised by Dr. Adnan Saud. His research focuses on the computation of robust controlled invariant sets and their applications to model predictive control. He also serves as a math education fellow at UM6P. Okay, without any further ado, please take it away.
So good afternoon, everyone. So yeah, I don't know if you are in the morning or it's afternoon, but for me it's in the afternoon. So I am Emmanuel Junior Wafo Wembe. So as Sakasha already said, I'm a PhD student at Mohammed VI Polytechnic University under supervision of Professor Adnan Saud. So today I'm going to present our works on what we call a trajectory-based characterization of robust control invariant set. So this is kind of like this is a group of work. So now, so this is will be the outline of the talk. So we have essentially two main parts. One we're focusing on monotone system, and the second time we work with linear systems. So first of all, control invariance is it's the property that set has to be where trajectory that are initialized within the set will remain there for all time as t goes to infinity. So now, why are those type of set interesting? Is because when we model safety constraint as set, having a subset of the safe set that is invariant guarantees kind of give us a certificate of safety. And this is why computing those sets is very important. So as such, I said that computing control invariant set is important. As already said that. So there is a large amount of work in the literature that deal with control invariant sets. So they range from continuous time system to discrete time system, and the type of method that we use depend of there have been many approaches that we use. We have Leponos-based techniques where we can find a great introduction in the work of Bianchini and the security approach to control invariance, and we have a reachability method that are quite recent. And also we have like we have optimization based technique using for example linear system. We have linear programming and semi-different programming for linear systems, and we also have iterative algorithms uh, from for linear and piecewise IP systems. So the most of these methods were using the property of control invariant set as sets to characterize them. So in this work, what we want to achieve, we want to use trajectory as a characterization of control invariance. So, and to do so, we'll look at two classes of systems: monotone system and linear time invariant systems. So, first of all, monotone system are dynamic system for which the the response of the system conserve partial order with respect to initial condition and input constraints. Sorry. So yeah, so this type of systems can be seen. They have a wide range of application. They can be seen in traffic networks and biological systems, and also when we want to check a system is monotone, we have a pretty good result for when the dynamic is is differentiable, which is called the chemical Muller conditions. So in this one, what we wanted to find control invariant for monotone systems, and the class of invariant set that we are interested in is the what we call lower closed set. Basically, we want all we want a set just that when I take all the points that are below the set using a partial order, I will still remain in the set. And so when we have a lower closed set, we have what we call maximal elements for this type of set. And maximal element characterize what we call element that cannot be compared to any other element in the set. So that means like they are either greater or they cannot be compared to each others. So since we are so like this is sorry. So now, as I said earlier, control invariant, we want the trajectory to remain within the set as time goes to infinity for all t. And so uh, this property kind of like a match is doesn't change if I use union of if I go from a set to a union. So the set of control invariant set is closed on the union. So if it's closed on the union, we since the union is kind of like it's a monotone operations. This we have the existence of a maximal control invariant set, and so this so we have the maximal contain just a set that contain any other control invariant set. So as I said, we want to develop trajectory-based characterization of control invariant set, and so the tool that we use is what we call monotone phasic trajectory. The idea is simple. Just want to the system to be steered in such a way that uh, at final time we are below all the previously explored points. So that we want to be below below the trajectory at the final time. We want to below all the trajectory, and so uh, so what does it mean? So how does it link to control invariance? So the idea is that if I have this trajectory, since this point is below, and if I take the set of points, the lower closure of the trajectories, so and then this lower closure will give me a control invariant set. So this is our first main result. So basically, if you have so if I take into account the fact that we can have so the so this set here, but set K, we give us the control invariant set for the trajectory, and also uh, this property is kind of like it's kind of easy to check because if the set is a multidimensional interval, we can drop the big D and just use D max. So that means we just have to look at kind of like just one trajectory of the systems. And so that's why we use the idea that we can group these to just the maximal element when to derive an algorithm to compute control invariances for monotone systems. The main idea is that if it I take a point in the safe set, I just look at the trajectory. Can I find a trajectory? I look if the point will always lead to the unsafe set, no matter what is the control input that we have. So then if the point is unsafe, and if the point is unsafe, all the points that are above the trajectory are also unsafe. Now, if the point is feasible, so we have like so the point eventually go below its trajectory. So that means this so that means we all know from the theorem that we have the lower closure is a control invariance. So if you repeat this procedure in this region, we can we can have we can compute robust control invariant set that are close to the maximal control invariant with up to a certain precision. And so we apply our algorithm to this system that is a control the coupe tank from the coupe tank. So the idea you want the water level in both tanks to not be be above a certain level. We want it to be below a certain to be below a certain level. And so we apply our approach to we compute two invariant sets with different precision. So this one, the precision here is 1, and here the precision here was 0.5. And in terms of computing so here we found three feasible trajectory. Here we found 4 feasible trajectory. So now both of these sets were easier to compute than to represent. So that's kind of so in this way, this approach seems very, very computationally efficient. So now we want to extend this approach to linear system, especially continuous system. So a continuous system. So the first step we want to look at the problem from the perspective of in the discrete terms. So this is a dynamic that we consider. So so in discrete terms, the control invariant definition change. We don't instead we don't need to look at all the full trajectory. We only need to look at the successor, the next state. So in this case, what we look at we kind of like, since we are looking at linear systems, we decide to modify the definition of feasible trajectory to be more in line with what we expect for linear system. And the modification we found that was reasonable was to change the lower closure operator to the convex solve. And so if you have so that means so basically differently. So what we want is that the final state is in the convex solve of the previously reachable state, visited state. And so if you have this definition, so if we find this trajectory, we can see that if I take a point in the convex in this convex solve, if I use a convex combination of input from point in this set, I will see B in the convex closure after. So that means the set is a control invariant. So this gives us this is our second characterization of control invariant using trajectory. So now, so for monotone system, the trajectory that we use was exploratory. We were kind of exploring the state space and see what trajectory, if we can find what those trajectory. Yeah, we decide to use optimization as we have a linear constraint. The timing was linear, so and in terms of representing as an optimization problem is quite easier. So the way we did that, we first suppose that the constraints are polytope. So that means we can have the set of vertices is finite, and so that means for in order to account the effect of this of perturbation, we use this. So we compute the next the next step as the convex solve of this di plus 1, and then we have the convex solve of di plus the state of the system that is of the unperturbed system without perturbation. So yeah, so that is why we can see this in this optimization we have mainly we can divide it into three groups of constraints. We have this these two are just these two constraints represent the first condition for feasibility. So if I go back, so we have this condition. You want the risk subset to be in X. So these two conditions guarantees you have the first condition. Now, if you have the second condition, this second condition guaranteed to have the is a way to rewrite the convex solve constraint using definition of convex solve. This condition represents the convex solve. And finally, this condition just we want to maximize the size of the set that we are the size of the constraint rate. So basically, what we are saying that we want that the distance between we want that the full safe set is included in the convex solve plus a ball plus a polytop plus a small polygon. So you want a small polygon to if I add a small polytop to the computed set, I can get the full safe set. And so we saw that this our approach. So we want to accelerate. So the approach was kind of like was already. So we found a way to compute component variance, and we want to. And then now we also saw that we can apply our result to model project control, in the sense that in traditional model control, this condition is generally x and t is in some set, and we want the set to be a control invariant that we have to compute before we use the MPC. And so what this formulation so by modifying this constraint to this one, what we get is that we don't need to compute the control invariant set a priori, so before applying the MPC, but we can get reverse feasibility. We can get reverse feasibility. We can just use the convex solve constraint. The convex solve constraint with the convex solve constraint, we can get recursive feasibility of the problem without computing the invariant set a priori. But as you can see, convex solve constraint lead to bilinear equality. So this one we can only apply it for the first iteration. So the thing is, if you apply it only for the first iteration, we get a control invariant set at the first iteration, and we can use that control invariant set for the next for the follow-up iterations. And in this case, we can still get the same. We can still keep the recursive feasibility without losing on speed, in terms of speed. So now I presented convex feasibility, and now I want to. And also we want to application to MPC. So now I want to show our approach to some examples. So now, we first apply the algorithm to the double integrator. So this is this dynamic system. So we want to double integrate the control. And so we used an horizon n equal to 20. So we were able to find this trajectory, this feasible trajectory. So this point here, this is the initial point, and we can see that the final set is in the convex hull of the previous set. And now we solve this problem repeatedly to get this final control invariant. And when we have the control invariant, we can apply any control that remain in this set, because we know that we have guaranteed that the set is control invariant, and so we just I just compute the control, and we can see that for this system, the control is quite stable. The control tend to stabilize the system. The control that we compute was tended to stabilize the system. So that's one. That's all. Now I showed that we can have a reducibility for MPC. So now we apply the MPC problem to this system that's called the couple tank. It's also another couple tank. So the idea is to find the tension in these two pumps, so that we can reach a targeted configuration of the system. And so we use from this initial point, we show that we can see that the trajectory was able to reach the target point as time goes by, and we can also see that we reach it quite fast with only 50 iterations. So now we want to complexify the task. So in the previous problem, we wanted just to reach a reference state. Now we wanted the system to follow a reference trajectory. And in this context, so we can see that applying applying our strategy, we're able to guarantee that we were able to follow the reference trajectory, as well as guarantee recursive feasibility of the problem. And you can see that we also reach we kind of converge fast, so in about 50 iterations in both cases for the problem. So we have seen two trajectory-based characterizations for risk invariant, one for continuous time monitor system, and the other for linear time discrete systems. And also we use those characterizations to develop two computational approach to the computation of control invariant set. One using exploration and multidimensional binary search, and the other using optimization. And we also show that our approach can be used in model predictive control to develop online recursive feasible scheme without the computation of control invariant set a priori. And so now, so in this work, now what remains to show is that we have seen that if we can find a feasible trajectory, we have the existence of we can guarantee that the control invariant exists. Now we are still looking at the reverse question. If there exists a control invariant, does a feasible trajectory necessarily exist? And finally, now, since you see that our approach use forward direction, we are kind of looking at the problem from a forward direction. So, and we see that in the first problem we use exploration to compute the event set. Can this approach be used for data-driven systems when we only have access to data and not the dynamic of the system? Can we in the case where we have an oracle, develop algorithms that can derive compute control invariant set from the output of the oracle. And so we have developed both discrete and continuous time characterization. So now is it possible to look at it from the perspective of hybrid systems where we have both uh, continuous time and discrete time dynamics. So thank you for listening. So
thank you for the great talk, Emmanuel. So do we have any questions from the audience? Maybe we can start to take them as we transition to the next speaker. So maybe let me give Mira access. Any questions from the audience? Looks like there's a question in the chat. So from Othman, he's asking, here you studied the discrete case, but how about the continuous time case? Was it already dealt with in the theory? So this was actually one of my questions as well. So you kind of studied this LTI discrete time system. Does the same, do you suspect that the same things might hold in the continuous time case?
yeah, but I think for discrete time for linear system, it's kind of like we have like it's kind of like we have something that's quite different, because if you look at from the point of stability, if you are that for discrete system we need to be in the ball of the ball of radius 1, center is 0 for the eigenvalues, whereas in the continuous case we need the real part of the eigenvalue of the system have to be still negative. So this dichotomy makes it that it can be quite challenging to extend the result. But I think, for example, if we use we can have, so basically there's an easy case where we can see that if you have we can have it for continuous system if we use zero order discretization, the ZOR discretization. So if you use ZOR, we can see that if you have if you find a convex feasible for the discrete version of the system, we have a feasible trajectory for the continuous version of the system. That's kind of I think that this kind of this is the easy part. But I don't know if kind of like if we can show it in the general sense.
Got it. Thank you for the great talk and for answering the question. So next we can maybe transition to the next speaker. So can you try sharing the screen, Mira?
Yes. Tak. Okay, I think.
Yes, we can see.
Okay, great.
Okay, so our second speaker is Mira Khalil. She has been a PhD student in automatic control at CNRS Green Université de Lorraine Nancy in France since 2022. She received a master's degree in electrical and electronics engineering and the master's degree in technology of communication, medical, and industrial systems from the Lebanese University in Lebanon in 2022. Her research interests include electrochemical batteries, observer design, Lyapunov stability methods, and hybrid systems. So without any further ado, please take it away.
Okay, thank you, Akash. So today I'm going to present a work that I did in collaboration with Romain Postoyan, Stéphane Raël, both of whom are from Université de Lorraine in France, and Dragan Nishik from University of Melbourne in Australia. And in this talk, I'm going to present a hybrid estimator for the, say, estimation of lithium-ion batteries. So lithium-ion batteries are adopted in many applications, from small consumer electronics to large electric vehicles. Their widespread use is due to the many advantages they present. They have one of the best energy-to-weight ratios, high power density, low self-discharge, which means that they lose charge very slowly over time when not in use, and no memory effect, meaning that their capacity is not reduced due to being repeatedly recharged after being only partially discharged. However, these batteries are prone to safety risks. For example, in 2013, a fire broke out on board a Boeing Dreamliner due to a malfunction in the battery. They can have a negative ecological impact, for example, due to the extraction of the battery material, and most importantly, they require a battery management system, or BMS for short. The role of the BMS is to protect the battery against safety risks like overcharging and over-discharging the battery, to prevent the battery from premature aging, and to enhance the battery performance. The BMS does this mainly via monitoring battery variables, which can be either measurable via sensors like the current, the voltage, and the temperature of the battery, or unmeasurable like the state of charge, or SOC for short, which is simply the percentage we see on our smartphones. So for these unmeasurable variables, we need estimation tools, and in this talk, I will focus on the state of charge estimation functionality of the BMS. There are two main ways to estimate the state of charge of a battery. The first one is by using open loop techniques. These are usually simple, but they are prone to cumulative errors. For example, column counting is a well-known open loop method to determine the state of charge. As we can see here from this equation, it estimates the state of charge by integrating the current of the battery, denoted here by I. There are several drawbacks to this method, the first one being that the initial state of charge needs to be known. However, this quantity can only be determined if the battery has been at rest for a sufficient amount of time. The parameter Q, representing the capacity of the battery, changes over time due to battery aging, and the current I of the battery is affected by measurement noise. So all of this results in errors that accumulate over time, leading potentially to an imprecise state of charge estimation. So overall, the main drawback of open loop techniques is the absence of a corrective mechanism against uncertainties and noise. And this is what motivates the adoption of observer-based approaches, which are closed loop as they incorporate a correction mechanism in their design. These are usually more complex, but they typically provide a better estimation accuracy and robustness against noise and disturbances. They consist on having a battery model and then designing an observer based on that model. Once the observer has been designed, we can drop the battery model and hook the observer to the actual lithium-ion battery. The majority of state estimation schemes for lithium-ion batteries are constructed for a single lithium-ion cell. However, in practice, a battery consists of several cells interconnected together in order to meet the voltage and capacity requirements of applications. If we take an example of a battery that consists of n cells interconnected together, a direct way to estimate the state of charge of the battery would be to design one observer per cell. We would end up having n observers where the dimension of each one would be at least equal to the dimension of the considered cell model. So if we consider, for example, a lithium-ion cell model of dimension m, then the global observer of the battery would be at least of dimension n times n. We notice here that as the number of cell n increases, the dimension of the global observer also increases, potentially leading to computational issues once the observer needs to be implemented. And this is the reason why we need low-dimensional estimators, specifically for multi-cell batteries. So one approach to reduce the computational demand of the state estimation of multi-cell batteries is to only estimate the state of the cells that have the limiting state of charges. And here, by limiting state of charges, I mean the minimum and maximum state of charges, and this is because given these two quantities, we can ensure that all the other cells have a state of charge within the operating limits. The challenge with this approach is that the cells that have the minimum and maximum state of charges cannot be determined directly by measurement, and furthermore, these cells may change over time. So the simplest way to tackle these challenges is just to consider the cells with the minimum and maximum state of charges are the same cells with the minimum and maximum voltages. And this is due to this equation of the voltage of cell I and the battery. We can see here that it is equal to a nonlinear function of the state of charge of the cell plus three terms, one due to the transient behavior of the cell, another due to the internal resistance of the cell, and the third due to the measurement noise on the voltage of the cell. So with this cell identification method, we are ignoring all the terms in magenta, and since VOCVI is usually a monotone increasing function for most lithium-ion technologies, then it is reasonable to consider the cells with the minimum and maximum state of charges are the same cells with the minimum and maximum voltages. This cell identification method is mostly adopted in industries and also some other works in the literature. There is works in the literature that try to refine this style identification method by incorporating more of the terms in magenta. However, as far as we know, none of them provide analytical guarantees on the estimation. So the objective of this work was to propose an estimator that has a low dimension and that has analytical guarantees on the estimation, specifically for multi-cell batteries. And this is exactly what we were able to do. In particular, we have proposed a novel hybrid estimator of the minimum and maximum state of charges. This estimator is hybrid due to the continuous time dynamics of the battery model and the jumps that are due to the change of the cells with the minimum and maximum state of charges. This estimator has a dimension independent of the number of cells, making it attractive for large batteries, and also it has global robust convergence guarantees on the estimation. So this was the introduction. Next, I will talk about the considered battery model. Then I'll present the estimator. Next, I'll give a numerical example before I conclude the presentation. We have considered a battery that has n cells interconnected in series, and we modeled each cell by one resistor capacitor equivalent circuit model, or ECM for short. In this rectangle, we can see the equivalent cell model of cell 1. It consists of an internal resistance, a parallel resistor capacitor branch, and an open circuit voltage that depends on the state of charge of the cell. One thing I would like to mention here is that even though we are considering cells that are modeled by equivalent circuit models consisting of a one resistor capacitor parallel branch, the result that I'm presenting today can be extended to cells modeled by equivalent circuit model that have many resistor capacitor branches, which are usually more accurate. So these are the equations that describe the dynamics of a cell I and the battery, where URCI is the voltage across the parallel resistor capacitor branch, SOC I is the state of charge of the cell I, and VI is the voltage across the cell, and I is the current passing through all the cells as they are in series. We notice here that the state dynamics are linear, and we only have a nonlinearity in the output equation, namely VOCVI of SOC I. We make two assumptions on each cell model. The first assumption we make is on the parameters. We consider that the parameters in magenta are all known, while we make no assumption on the parameter to the I in blue. The second assumption we make is on the nonlinearity VOCVI of SOC I. We assume that it is known for each cell and that it satisfies the following property, which basically says that VOCVI is monotone increasing with a minimum increasing rate. This assumption is satisfied by many lithium-ion technologies, as we will see later on in the numerical example. So given the series interconnection of the cells and the dynamic of each cell in the battery, we can derive the following state space model, where X is the concatenation of the state of each cell, where the state of a cell I in the battery consisting of URCI, the voltage across the parallel branch, and cell I, the state of charge of the cell. And therefore, the dimension of X is 2 times n, with m being the number of cells. The input to the state space model is I, the current passing through the cells, and the output is the concatenation of the cell voltages plus Fv, where V represent the measurement noise on the voltages. We also add to the state dynamic the parameter, the variable W, to represent disturbances, accounting for modeling uncertainties. Now I'll present the hybrid estimator. Again, as I mentioned in the introduction, the objective is to estimate the minimum and maximum state of charges, as with these two quantities, we can ensure that all the other cells have a state of charge within the operating limit, thereby ensuring the safety of the battery and preventing it from premature aging. However, the cells with the minimum and maximum state of charges cannot be determined directly by measurement. For this reason, we choose to introduce two selection variables that we call underlying sigma and overlying sigma, and that take value in 1 to n. The role of these two selection variables is to select the cells that potentially have the minimum and maximum state of charges. So how does these two variables do so? We have yi representing the noisy measurement of the voltage of cell I given by this equation. By first isolating the term VOCVI of soc I, then exploiting the fact that VOCVI is invertible, we can obtain that soc I is given by this equation, where the terms in blue are all known under our previously made assumption, and the terms in magenta are unknown. From this equation of soc I, we introduce what we call fast estimate of the state of charge of each cell, that we call here soc I hat, by simply ignoring the noise term on the voltages Fv and introducing an estimate of URCI that we call here URCI hat. So based on this equation, we can then choose the selection variables underlying sigma and overlying sigma to be the cells that have the minimum and maximum soc I hat in the sense of this equation. So two questions arise from this slide. The first one is, how can we estimate the URCI of each cell in the battery without having our estimator dimension depend on the number of cells? And the second one, when do we need to update underlying sigma and overlying sigma? The first question is answered on this slide. The hybrid estimator is defined such that in continuous time, he runs the following dynamics of an intermediate variable that we call URC bar. And this intermediate variable, URC bar, has a dimension equal to 1, and dynamics similar to the dynamics of URCI of each cell, with the main difference being in the parameter τd, which is a design parameter that we introduce. For example, if the TODIs of all the cells are known, TOD can be taken as the average of these parameters. And from this intermediate variable that is run in continuous time, we can then produce an estimate of the URCI of each cell by simply multiplying it by a constant associated to each cell. Furthermore, in continuous time, cells underlying sigma and overlying sigma remain the same, and we run the following dynamics of the variables soc underline hat and soc overline hat, which are estimates of the minimum and maximum state of charges respectively. These variables dynamics are made of a copy of the dynamics of the state of charge of cells underlying sigma and overlying sigma respectively, plus a correction term where L1 and L2 are positive gains of our choosing. On the other hand, the estimator exhibits a jump when either cell underline sigma or cell overline sigma needs to be updated. For the case when cell underline sigma needs to be updated, the variables underline sigma and soc underline hat change for them to be the cell with the minimum soc I hat and the minimum soc I hat, respectively, in the sense of this equation. While for the case of when cell overline sigma needs to be updated, the variables overline sigma and soc overline hat are a change, while all the other variables remain the same. Now I'm going to present the switching logic of the hybrid estimator, which will tell us when do cells underline sigma and overline sigma need to be updated. And in this slide, I will focus on cell underline sigma. So cell underline sigma remain the same when all the cells have a soc I hat in the sense of this equation greater or equal than the estimated minimum state of charge produced by the hybrid estimator. However, cell underline sigma changes when there exists a cell that have a soc I hat in the sense of this equation equal to the estimate of the minimum state of charge produced by the hybrid estimator. We add to the switching logic the parameter epsilon in order to avoid having an infinite amount of jumps infinite time. And we also add the parameter mu for the case when underlying sigma changes in order to enlarge the set and avoid it being of Lebesgue measure 0, which is undesirable in practice. A similar switching logic can be interpreted for cell overline sigma, in which I do not present explicitly. In this slide, I summarize the continuous time dynamics of the hybrid estimator. Again, in continuous time, cell underline sigma and cell overline sigma remain the same. And this means that the inequalities in the set C1 and C2 are satisfied. We notice here that the dimension of the hybrid estimator is equal to 5, including the dynamics of cell underline sigma and overline sigma, which are just constants, while our battery model was of dimension 2 times the number of cells. So with this, we have achieved our first objective of designing an estimator who has a dimension independent of the number of cells, making it computationally attractive for large batteries. In this slide, I summarize the discrete time dynamics of the hybrid estimator. The estimator exhibits a jump when either cell underline sigma and overline sigma needs to be updated, or in other words, when the inequalities in D1 or the inequalities in D2 are satisfied. The second objective of this work was to provide an estimator with stability guarantees, and in particular, we were able to show that the estimated minimum and maximum state of charges, soc underline hat and soc overline hat, produced by the hybrid estimator exponentially converges to the minimum and maximum state of charges up to an error due to 4 terms. The first one is due to the presence of epsilon in the switching logic. The second is due to the difference between the design parameter of the hybrid estimator TOD and the parameters of the cells, the TODIs. The third one is due to the presence of disturbances, and the fourth is due to the measurement noise on the output. Furthermore, we have showed that there exists an average continuous time between 2 successive jumps under mild conditions on the inputs, and there can only be at most 2 instantaneous jumps, one due to the update of cell underline sigma and the other due to the update of cell overline sigma. So now I'm going to give a numerical example. If we considered a battery with 200 cells interconnected in series, where each cell, we represented it by an equivalent circuit model with 3 resistor capacitor branches, and therefore the battery model was of dimension 3 plus 1 times 200, which is 800. We considered that the cells have different parameters from normal distributions with 10% dispersion from nominal values, and we considered them to have different initial state of charges and different nonlinear functions, VOCVI, between the upper and lower bounding one that we see here in this figure. We notice here that the nonlinear function satisfies our previously made assumption of it being monotone increasing with a minimum increasing rate. We apply the following plug-in hybrid electric vehicle current profile to the battery, which is at a first time interval on average discharging, at a second time interval on average charging, and at a third time interval equal to 0. And we add the following bias on the input current of the battery and the following measurement noise on the voltages of the cell. So these two figures shows the index of the cells having the minimum and maximum state of charges and cells underlying sigma and overlying sigma identified by the hybrid estimator. We can see here that that cell underlying sigma correspond most of the time to index of the cell having the minimum state of charge, as well as here cell overlying sigma correspond most of the time to the index of the cell having the maximum state of charge. Furthermore, in this figure, we show the minimum and maximum state of charges and the estimated minimum and maximum state of charges. We can see here in the lower figure that the error, overall the error is small. Therefore, the hybrid estimator is capable of producing accurate estimates of the minimum and maximum state of charges. We have also compared our cell identification method with the method that I previously mentioned in the introduction of considering the cells with the minimum and maximum state of charges are the same cells with the minimum and maximum voltages. We can see here that the hybrid estimator is performing far better for the identification of the cells with the minimum and maximum state of charges. Indeed, here that the cells having the minimum and maximum voltages are frequently switching, which may be undesirable in practice. Moreover, we have showed in this figure the minimum and maximum state of charges estimated by the hybrid estimator and those given by the voltage-based method, identification method. And we can see here that our hybrid estimator produces more accurate estimates of the minimum and maximum state of charges. So with this, I have reached the end of my presentation. Again, we proposed a hybrid estimator that has a dimension independent of the number of cells, which making it attractive for large lithium-ion batteries, and that has robust global convergence guarantees. This work, a primary version of this work was presented at CDC in 2024 and is being published in Automatica currently. There's, of course, more that can be done to improve the estimation of the state of charge for multi-cell batteries. We can start by first experimentally validating the proposed algorithm in real time to perform parameter estimation in order to relax our previously made assumption and to incorporate thermodynamics in our design. So thank you for listening, and this is the end of my presentation.
Thank you for the thank you for the very interesting talk. So do we have any questions from the audience that we can take? So I can ask a question. So I think you assumed you had knowledge of these battery parameters, I think like this capacitance and these resistance, for example.
Yes.
So is this something that ever changes during the life cycle of the batteries? And if so, is that something that you can maybe like adaptively sort of tune based on some estimates of the system?
Yes, these parameters, for example, the capacity here changes with the battery aging and the temperature. So yeah, it's possible that maybe you can do some adaptive way of like I know there exists, like for single cell batteries, there exists some adaptive observers in order to take into account the parameter variation. But for multi-cell batteries, not yet. So yeah, so I'm not sure, like in the context of multi-cell batteries, what can be done, because are you gonna estimate the capacity for each cell, or are you gonna consider the extreme values of the capacity depending on the temperature? I think it needs to be reflected on and thought about, at least for the case of multi-cell batteries.
Gotcha. Yeah, that makes sense. I guess like you're trying not to add too many parameters to your estimator.
Yeah,
so somehow,
exactly.
no,
Yeah.
got it. Any other questions from the audience? All right, then with that, I think we're finished for today. Thank you for the great talks to both of our presenters. So then the last seminar will be taking place 2 weeks from now before CDC. So I hope to see you all there. Thank you all for coming and have a good day.
Thank you.